Hi, this is Dr. Satish, Assistant Professor at British Applied College. I welcome you all to my video lecture. This is for ENG208 Mechanical Principles, Pearson Higher National Diploma unit for mechanical engineer students. Now, in today's lecture, we will see how to find reaction forces, how to calculate the reaction forces for uniformly varying load. In my previous lectures, I solved for point load, for uniformly distributed load. Now, we will look into how to solve for a uniformly varying load. Now, in the screen, you can see a problem. Okay, a simply supported beam. So, you have two reaction forces and a uniformly varying load. Okay, so the triangular load you can see, and as I said earlier, please look into the unit. Okay, the unit here is kilonewton per meter. Okay, so the weight, this is may be my weight intensity. Now, the total load acting because of this triangular load will be, it can be calculated by area. Okay, area of the triangle. Okay, so the total load will be area of the triangle, which will be half into the breadth. Okay, so when I say about the breadth, it is 3 meter, so it will be 3 into now the height, so it will be 6 kilonewton. I will just write 6 now, I'll later add kilonewton later. So this will be 9 kilonewton. Okay, so my total load will be 9 kilonewton. Okay, just as a quick refresh, if you see the total load in our previous lecture, okay, for uniformly distributed load, the total load was supposed to be just multiplying this 6 kilo, I mean I am just multiplying the 6 kilonewton per meter into the length. Okay, I will be just multiplying the length, so 3 meter, so finally it will be 18 kilonewton, which is what I used in this equation. Okay, now how to solve the reaction forces for such a problem. So the only difference, okay, the only difference between a point load, a uniformly distributed load and uniformly varying load is the total load. Okay, the total load acting and where, okay, where the point of action is. So this is the line of action is. Okay, so this is what the difference is. Once you understand this difference, then things will be easy for you. So like any other problem, I need equilibrium equations, okay, to solve this. So my equilibrium equations will be summation of forces along the x-axis should be 0, summation of forces along the y-axis should be 0, and summation of forces and summation of moments, okay, at any point, okay, should be equal to 0. So as you all can see, there is no horizontal forces. I have vertical forces and only vertical forces, and so I cannot use this equation. I will be using only these two equations. Again I am repeating, if there are two unknowns, okay, you definitely need two equations to find unknowns. Now let me use the first equation, summation of Fy is equal to 0. Okay, I will take all the forces acting upwards as positive. Now in this case RA will be positive and RB will be positive. Okay, so just now we found the total load because of this weight intensity is, because of the uniformly varying load is 9 kilonewton. So I will just give a negative sign and write it here. So because the reason why I give a negative sign is because it is acting downwards, I took upward as positive. So now RA plus RB is equal to 9 kilonewton. So this will be my equation 1. And in the second equilibrium equation which I will consider is sigma moment at any point equal to 0. Okay, so let me consider point A. I am considering point A. So if I consider point A, the forces that will cause moments are the load, the applied load, and the reaction. Okay, these are the two forces that will cause moment. Okay, RA will not cause a moment because it is acting at the same point. If a load is acting at the same point, it can cause only translation. No, it cannot cause, if a load is acting at the same point, only it can cause translation. It cannot rotate. Okay, please understand that. Fine. Now, I will consider anti-clockwise as positive. And if I write my equations, I have first let me write for RB. Okay, so RB is at a distance of 5 meters away. So, and this application, if I apply RB, okay, it will cause an anti-clockwise rotation. So, I will write RB into 5, okay, because moment definition is force into distance. So, I will give positive. And this one. So now you have to understand, for uniformly varying load, for a triangular load like this, the point of action, if I consider an equivalent concentrated load, okay, if I consider an equivalent concentrated load, then this load acts, okay, maybe I will use black color. This load acts at such a distance such that it is 1/3 from the head of the triangle and 2/3 from the tail. So please understand. So this is where this is the line where the total load will act, if a equivalent point load will act. Okay. So the distance of this equivalent point load from A is 1/3 of the total length. Okay, so 1/3 of 3. So if I write this, then I have to write first my load is 9 into 1/3. Okay, 1/3 of the total length. Okay, 1/3 of total length is 3. So I can just write the sign. The sign is, if I consider the body about point A, the load is acting like this, so it will cause the body to rotate in the clockwise direction. I consider only anti-clockwise as positive, so I give negative sign here. So finally this will be equal to 0. So for RB is equal to, so this one gets cancelled, so 9/5. Okay. So this is how we solve for it. So the answer is 1.8 kilonewton RB. Okay, if I substitute this, if I substitute RB is equal to 1.8 kilonewton in equation 1, so I will be getting RA as, so 9 minus 1.8, which is supposed to be 7.2 kilonewton. Okay, if I want to cross check, okay, then quickly we'll do it. The load is acting towards RA, so RA's reaction will be more compared to, the magnitude of RA will be more compared to RB. So that is reflective in my answers. So obviously my answer is correct. Okay guys, thank you all. Let me see you all in the next video.